So this autopilot system is working independently, and as you can see, like as I'm opening my mouth or reducing the distance between my eyelids, it's showing me a drowsiness alert, and that same alert is copied onto on the top of the video that is displayed for the car. And currently, in our scope of the project, we weren't able to achieve an autopilot system which could actually predict the acceleration and braking of the car. So we weren't able to slow down the car or anything, but we were able to successfully integrate these two. And based on this architecture, we are hoping to improve upon it and add acceleration prediction, brake prediction, and gear change predictions. So as you can see below, the steering wheel is rotating as the car is making a turn. And I think we are limited on.
Hello, I'm Zoe Cui, and for the final project, our topic is to combine autopilot auto-driving with drowsiness detection. This is because drowsiness driving is really dangerous. The U.S. National Highway Traffic Safety Administration reports that drowsy driving resulted in almost 100,000 road accidents and more than 1,500 deaths per year. As we can see, this is a huge amount, and drowsy driving is responsible for 30% of all road accidents and 20% of all vehicle accidents. And although now we can use autopilot to achieve auto driving, it still has a few problems. First, the system don't always work in complicated environments. They require monitoring. And if the driver gets sleepy, they are risky to be involved in an accident, and they are still responsible for that car. And the accurate steering is the first step toward drowsiness detection. As a result, we decide to combine drowsiness detection in a autopilot auto driving system so that we can improve the user's experience while driving and improve the safety level, avoid some accidents. And one of the signs of exhaustion is yawning. When yawning, the mouth is wide open and larger than when we are speaking. So one can identify yawning by detecting the face and then the mouth. And in the first related paper, the author developed the yawning detection system based on the open rate of the mouth and the amount of changes in the mouth contour area, as shown in this figure. Another sign of drowsiness is unusual eye blinking rate and eye closure duration, because when the driver feels sleepy, the frequency of blinking will be lower and the gaps between eyelids are less than normal situations, so we can easily detect drowsiness. In this paper, P. Smith implements blink detection. They automatically initialize eyes using color predicates and connected components, then track eyes with a fine optical flow and color predicates, and determine blinking and eye disappearance using the number and intensity of pixels in the eye region. So in the third paper, the author used the leaf to detect face landmarks, and then they used those landmarks to calculate eye-related features, and they use those eye-related features to build a blink detection model. And this paper performed very well. They got 82% accuracy. It's even higher than humans' performance on the same dataset. So inspired from those three papers, we decided to use the lab to detect landmarks and calculate the eye-related feature and mouse-related feature to detect drowsiness. And David proposed an end-to-end self-learning system for self-driving car that involved training a convolutional neural network to map raw pixels from a single front-facing camera directly to steering commands. This approach provides surprisingly powerful. With minimal training dataset from human, the system learns to drive the traffic on local roads without landmarkings and on highways. The system automatically learns internal presentation of the necessary processing steps, such as detecting useful road features with only the human steering angle as the training signal, and the Autopilot system we are targeted and built is inspired from this paper. I aim to improve the system by adding synthetic data training along with the real-world data.
Here is the drowsiness detection. We use the Ellipse framework, which can be trained to predict any kind of shape. And in this project, we use the pre-trained face detector, which is based on the histogram of oriented gradients and the linear SVM method. This is trained on the 300W dataset, and I attached the model link, which we use in the project. After having this model, we can predict the face shape and find out the region of interest. Then we can extract out the object landmarks, which is the specific area we care in the detected face. Here, the region of interest are eyes and the mouth, which we will elaborate later. In general, the landmarks produced by the lib are a indexable list. The indexes are shown on the right. We can see the numbers in the face. So, the eye is here from 37 to 48, and the mouth is 49 to 68. We can getting them by simply using the index. Once having the indexable list, we can calculate the feature for drowsiness. Here we use the EAR and MAR, which represent the eyes and the mouth features separately. And then there's the EAR, means the eye aspect ratio. We assume the person is sleepy when the eyes are closed. So we can use the eye feature to represent the drowsiness. This is, each eye is represented by 6 coordinates starting at the left corner of the eye. And we can find the P1 to P6 from the previous landmark list. And when the eye is open, the EAR is large and approximately constant. And when the eye is narrowed down or is closed, the this number approaching to 0, since the eye length is approaching to 0. And after having it, we can detect the drowsiness. We have the threshold like 0 to 0.8. And when the EAR is lowering than this threshold for more than 30 frames, we assume this person is drowsy. And after that, we can pass a value to the autopilot phase. And the reason to monitor more than 30 frames is to avoid any impact of the occasionally cases and the impact of the blinks, like the eyes are closed and open rapidly. So we only detect the drowsiness when the EAR remains low for enough long time. That's it.
Another feature we are using is MAR, which is mouth aspect ratio. This is because yawning is one of significant signs for drowsiness. When yawning, the mouth is wide open and larger than when we are speaking. And the MAR is basically the height of the mouth over the width of the mouth. As we can see in this formula, we calculate the average of the distance between P2 and P8 and P3 and P7, as well as the distance between P4 and P6. Then this average distance will represent the height of the mouth, and the distance between P5 and P1 can represent the width of the mouth. When the driver continuously gets a high MAR, we think he's yawning and he's drowsy driver.
Hi, my name is Aditya, and I'll be demoing our part of the project on Autopilot. So, generally, Autopilot systems are designed and developed to work with self-drive cars, and one such example is Tesla. They created an autopilot system based on different sensors, and they record all the surroundings using the cameras. So everything is put inside a convolutional neural network, and they are able to work with that autopilot system and give you a self-drive car that works really well. And to follow in its steps, we have also pursued an autopilot system, but we are coupling it with drowsiness detection, because if in case a driver uh, goes sleepy during the autopilot system being active, it might be harmful to his own health because the car might not know what to do in certain conditions. And we have built an end-to-end pipeline to cater to that. So we are working with two different data sets. One is real world data set that is gathered from the streets of California. And as you can see, this data set is curated using a camera put on top of a car, and it gives you a front view of the car while it's driving. The label of each image in the dataset is basically a steering angle of the steering wheel in radians, and that is like your y coordinate that will be fed into the convolutional neural network to predict. The second data set we are using is the synthetic data that is curated from the Udacity self-drive car nano degree, and this data set acts as a proof of concept, which shows us that you can indeed train a convolutional neural network to learn the steering angles of a car. Again, this dataset also contains the labels in the form of steering angle of a car in radians. So we went ahead and we built two different convolutional neural networks. One convolutional neural network works with synthetic data, and the other one works with real world data, as we have seen. And we use TensorFlow for building both of our convolutional networks. The reason that we pursued two different architectures was because we are using synthetic data as our proof of concept. We also wanted a different architecture to do that, and this architecture is much smaller than our main architecture. So these are the two different architectures that we have built. CNN1 is for synthetic data and CNN2 is for real world data. So CNN1 is built using 3 convolution layer, and that is part of its feature extractor. And to reduce the dimensions after each convolution, we are using max pooling. As you can see, the filter sizes increase from 30 to 64 and 128. And we are using a kernel size of 3 cross 3 across every convolution layer in the feature extractor. The stride is 1 and padding is same. So this feature extractor acts as a network which will output some features that will be essential to classify the steering angle of a car. And the outputs of all of the feature extractor is given into the classification module, and that is shown in table 2 classification 1. And we have gone with two different two hidden layers in the classification network. We have performed several experiments on top of these, and we can discuss that later. The CNN2 as shown is basically the convolution network which we have used to train on the real world data. So for this CNN, we are using 6 convolution layers, and we are using max pooling across all the layers, and the filter size is 3 cross 3 again for each convolution layer. And this is a big convolution network compared to the first network. The reason behind it is the real world data has much more complexity, much more features, and we would like our network to learn that, and the first network wasn't able to do that. So we went ahead and we built this one. The classification network in this case is a network with 3 hidden layers. These 3 hidden layers are again there to make sure that you don't lose any information necessary to actually predict the steering angle in degree. So we have conducted various experiments to train both of our networks. One was the training and validation split. So we tried the general training validation split, that is 80% by 20%, where 80% is the training split and 20 is the validation split. We also tried two other different splits. One was 90 training and 10 validation, and the other one was 70% training and 30% validation. So in the case of 70% training and 30% validation, we actually observed that the performance of both the networks gone down. And that might be because the training data was sparse and it might not have been shuffled properly. The result with the 90-10 split was that the no model that was trained on the synthetic data worked really well, whereas the model that was trained on the real world data actually decreased in performance. So in the end, we used 80-20 split for the synthetic one and 90-10 for the real one. I'm sorry, yeah, 90-10 for synthetic one and 80-20 for the real one. We also experimented with different dropout layers, adding them after each convolution layer or having a combination of them across both the feature extractor and the classification networks. The best way, we trained multiple epochs, and we also tried different p-values for it, that is the selection value. So the best result that we found out for our networks was having a dropout layer in between feature extractor and the classification module. And that turned out to be good enough for us to go ahead and experiment with different things. The next experiment that we did was for batch size. So generally we try to keep the batch size in the powers of 2. And that is because in powers of 2, it's generally acceptable for us as well as the network, and it is faster. The training is faster on the GPU because it's like entirely made of 2 power 32. Sorry, yeah. And again, we tried different things, but due to hardware limitations, we weren't able to go beyond a batch size of 64. Plus, having a greater batch size means we were training the network really slowly. So in the end, we went with batch size 32. And our main experiment was training different architectures, adding different convolution layers, trying different strides, padding, and different poolings. And we tried all of that, and we conducted over 400 experiments in total, I guess. And in all of these experiments, the networks that I've shown you before are the best that we found out to be true. And the other ones were either overfitting or underfitting, or in a case where the loss was simply not decreasing. So this is what we went ahead and did. So the results that we got was the synthetic CNN, I'm naming it that, was able to achieve a validation accuracy of 97%. And the real world CNN was able to achieve a validation accuracy of 84%. The inference we derived from this was it might be possible that the real world data did not come from a domain which was for the testing data. And because the testing data was again curated from random videos on YouTube, we couldn't really say that if there were California routes. Plus, it might be also true that the networks that we were trying were not complex enough to learn real world data features. So in the end, what we are hoping to do in the future is to build a bigger network, and due to hardware limitations right now, we weren't able to do so.